Yeah, welcome once again. So today we want to discuss about the first law of thermodynamics. What does the first law of thermodynamics says? So the first law of thermodynamics says that it is simply the another way of saying the law of conservation of energy, meaning energy cannot be created nor destroyed, but it can be converted from one form to another. You understand? Now you can convert energy from one form to what to another. So when you are talking about thermodynamics, you are studying a system. Is that taken? That is under thermodynamics. So if you now have a system whereby this quantity of heat is applied to it from the surroundings, then the system needs to give back a work done. So meaning that what the heat supply is that taken is equals to the integral, the closed integral of the work done. You understand? So one of its application now is now steady flow system. When we have what a steady flow system. So let us consider this now. What do we call a steady flow system? It is a special open system whereby matter flows in. Is that again? It enters in and comes out at the exit. You understand? We have inlet and the outlet. You understand? So in this case now, so we have what this diagram want to explain continuity equation. So in this case now, we have our inlet as well as the outlet. This is where the heat is applied from the surrounding to the system. Then work done is what is given back here. We have Q, that's heat supply per kilogram. Then W, which is the work done, will be out here. That's work done per kilogram. Now the C is now the velocity. Is that taken? The velocity of the fluid. Now the Z is the height above the datum. This is the datum, the horizontal ground. You understand? Now the pressure of the fluid is the P. So as it is now, is that taken? There will be a pressure gradient, meaning that the pressure will be decreasing. You understand? And we have the area of this portion that we want to look at, which is this one has A2, as in the area of this one is A1. Now U is the internal energy per kilogram. Don't forget that capital letter U is the internal energy. Is that taken? But when you are now considering what internal energy per kilogram, we have explained intensive properties, extensive properties, and specific properties. Is that taken? So you taking this one now, that the capital letter U divided by this will give you what? A specific. It's going to give you what? A specific this. So this is now the small letter, that's the internal energy per unit kilogram. So same thing goes to enthalpy. Normally enthalpy is capital letter H divided by M. So we have the mass flow rate. This is the specific volume, that's volume, actual volume divided by mass, and it gives you specific volume. This is the normal volume. That's the reason why I used another color. So this one, PV from Boyle's law. Is that taken? Boyle's law, that's PV. It is the unit gives you joules. Is that taken? So being joules, it is energy. So this is the energy required for 1 kilogram of the fluid. Now let us now consider continuity equation. Continuity equation. So in this case, from the inlet, we are going to have internal energy per unit mass. Is that again? Plus what's it called? Kinetic energy is half mc squared. We are using our velocity because we cannot use v here. Reason being that we have v and small letter v, so we cannot use v. So we take our velocity to be c. You understand now? Half mc squared. You understand? So but here, if you observe that this one is gotten from here, which is small letter. This is specific. You are being specified. You understand? So I have divided by m here. Is that taken? Because I'm using per kilogram. The mass has been annulled. You understand? So this one, kinetic energy is what? Half mc squared, and potential energy was mgh. You understand now? So our datum is now for the for the Z1, you can see the inlet. The inlet is Z1. Is that again? The outlet is Z2. Let's take notes. So here we are considering all the energies that we have in the system. The energy at the inlet is equals to the energy at the what? At the outlet. That's the continuity. You understand now? So now the kinetic is this. Now potential is what? mgh. So the g as the m will cancel m. Is that again? That's this one is not energy per unit mass. This one will now give me Z1g. You understand? Plus this is the energy of the fluid itself. That's P1 V1. This is small letter v. Please don't forget small letter v. Small letter v. So at the inlet, Q is applied. Now, what will now happen at the outlet? You know that we are going to have W. Is that taken? Plus internal energy. Is that taken? Plus half C2 C squared. C2 squared. Is that taken? Plus P2 V2. Is that taken? And finally, we are going to have our potential energy Z2G. You understand now? So in that regard, so we can call this one equation 1. You can call it equation 1. Equation 1. Okay, let's continue. So here we can bring this one and this one together. This one and this one. There is a reason for that. U1 plus P1 V1. They're together now. Is that taken? Plus because internal energy plus P1 V1, it will give you enthalpy. You understand now? So let me write it this way so that I will not be repeating. What happened? Okay, all right, sorry. So since H is equals to U plus PV, so we can bring this together. You can now say that U1 plus P1 V1 together now plus half C1 squared plus Z1G plus Q is equals to same thing here, U2 plus P2 V2, bring them together, plus half C2 squared plus each other one, Z2G plus work done. Is that taken? So this one can now be written as what? Equation 2. So let us now substitute. We are going to have H1 plus half C1 squared plus Z1G plus Q, which is the heat supplied. Now this one was H2, which is the enthalpy. Is that taken? Specific enthalpy plus half C2 squared plus Z2G plus work done. I hope I'm making sense. So we have the what? This energy to what? To be shrunk. But in this case now, what if now have what? A condition whereby the datum above, the height above the datum is now negligible. Meaning that if Z1 is equals to Z2, is that again? Our formula will now reduce to H1 plus half C1 squared plus Q. Is that again? Is equals to H2 plus half, don't forget the C is the velocity, plus W, because it is what? It is negligible. By the time you calculate, you bring this one together, is that again? Since it is negligible, to give you 0, then we now have what? This shrink what? Energy. So this steady flow rate, this steady flow system, is that it is applicable in diffuser, nozzle, even in compressors and pump. Yes, so these four, they are utilized there. So now let us consider mass balance equation. Mass balance equation What's the mass balance equation? Don't forget that from continuity, flow rate is equals to area times volume. Area, the area multiplied by velocity. Is that okay? We are not using V here now. Is that okay? So because some people are used to Q is equals to AV, where this one is velocity and this one is area. So by that, now let us look at the unit. What's the unit of area? That's meter squared based on SI unit. This one is meter per second. Then your final unit will now give what? Meter cube, then seconds. You understand now? So that's just it now. But mass flow rate, what is mass flow rate? Mass flow rate is equals to mass. This is specific mass flow rate, mass over what? Over time. You understand now? This one is now what? Kilogram, then seconds. You get? So here, this kilogram what? Seconds now. We can now relate mass flow rate as in m dot is equals to CA over V. Don't forget that your V is the volume here, specific volume here. You understand? And in that regard, so volume over mass. What is volume over mass? And you have what? Density is equals to mass over volume. This one is just what? The reciprocal of what? Of density. The reciprocal of what? Of density. Now back to this now. Don't forget that this one is what? The actual volume over what? Over mass. Meaning that the volume has m cube over kilogram. Is that taken? So if we go by SI units, what I'm saying is this. We want to look at this. The unit of what? Of mass flow rate. What's the mass flow rate? Mass flow rate is kilogram seconds. So does it align with this? Now this one is meter cube per second, which is your AC. That's the unit. You understand now? So divided by V. Now let us now work it out. This one is CA over V is now capital letter V over M. Now by doing that, we are going to have what? MCA over capital letter V. So what is this one is kilogram. This one is the two of them, MC. This is the unit. That's m cube seconds over what is V? The V is what? Meter cube. This cancel this. Then finally you have what? Kilogram per seconds. That's what you have here. So this formula is very important. So your mass flow rate is equals to CA over specific volume. I repeat, CA over specific volume, knowing that your specific volume is inverse of density. You understand? Now, the mass of the open system experiencing a steady flow process remains constant. Is that again? Meaning that what? The mass, the quantity of what? Of fluid that enters must be the same thing that what? That goes out. You understand now? So that's just it. Meaning that for m dot is the same thing as m dot 1 mass flow rate in the what? At the inlet is equals to the mass flow rate at the what? At the outlet. You understand now? So we cannot have our continuity, what our mass balance equation to now be m dot is equals to, this one become what? C1 A1 over V1. Don't forget this is specific volume, is equals to C2 A2 over V2, specific volume. Is that taken? Is equals to Cn AN over Vn, specific volume. Is that taken? That is what? The mass balance equation. Mass balance equation. We can as well have another one which we call energy balance equation. For energy balance equation, so for energy balance equation, stop there. Alright, thanks for watching. We'll continue in the next class.